Welcome all. If anyone wants to sit, there are still about 5 seats open for the 30 of you who are in the back. Thank you for sticking around. This is the last talk, I believe, of the day on this stage. Peter did a good introduction, so I'm not going to say much more in terms of introduction. At the Quanergy, we make solid-state LiDAR. That's our core capability, though we're also strong in software and full system integration. I had to show this slide. All of you who are here already know that we are what's called a unicorn, right? So that's part of what's interesting is that it's always exciting when us optical geeks manage to kind of find the right application and the right need and make it big in the business world. So our last round was we raised 90 million on 1.5 billion in pre-money valuation, and we're a couple of billion in valuation now. And our next event is the IPO. We have 130 employees. We'll be 200 by the end of the year. We are hiring lots of optical people. This is probably the strongest pool of talent anywhere. We have offices at 10 locations globally, listed here on every continent. Some of our partners are, some of our public partners, because in reality we have about 300 partners, but the ones who gave us the permission to mention their names are Mercedes, Renault, Nissan, Hyundai, Kia, Delphi, Koito. Actually, Koito is actually the largest headlight maker in the world, and Sensata, which is the former sensing division of TI. What makes us jump out of bed, although we sleep only 2 hours a day, is our mission, social impact of the company. We say that we do 5 things. We save lives, most importantly. We save space, we save time, we save energy, and we save cost. And that's very motivating for our team. We are active in 4, we call them pillars. A pillar is basically a group of applications. Transportation, broadly defined, it includes, of course, autonomous vehicles for passengers, but also trucks, trains, and the infrastructure that goes with them. Security, everything from smart home to smart borders. We were in the news a bit recently because of that. Industrial automation, which includes many applications in warehouses, in mining, agriculture, and so on. And 3D mapping, both terrestrial and aerial. Those are some of the applications that fall in the 4 pillars. The key point here is that in all cases, the solutions that a good LiDAR system provides should lead in cost, performance, reliability, size, weight, and power consumption. So why LiDAR? We all know why LiDAR. We're all optical people here. It's the only true 3D sensor. Sometimes people say, why not video, why not radar? Listen, you have 1D radar, which tells you how far something is, with virtually no information in X and Y on how big it is, what it is. It's just that it seems that there's an obstacle at such distance, right? That's a 1D sensor. But it's really good at it, very precise, it works in fog, it's really robust, but just 1D. Video is 2D. Now, in video perception, you have to analyze each 2D pixel array, frame to frame, and try to estimate how far something is, how big it is, how it might be behaving, and so on. And basically, the outcome of all that crunching is really a low quality version of the raw data that we can get with LiDAR. In LiDAR, it's all direct measurement. So we send laser pulses all around the sensor, and we get a 3D envelope of the environment that has centimeter accuracy up to 200 meters. So we don't have to do any processing to figure out how far someone is, how big they are, what they are, or how they are behaving. So in autonomous vehicles, everyone agrees that the most capable sensor is LiDAR, and the primary sensor must be LiDAR. And I would be more than happy to have a discussion if someone disagrees. But to make it commercially viable, even Elon Musk, who made some statements about LiDAR, who said, for instance, you don't really need a LiDAR, maybe it's too good for the job, especially when it's expensive, maybe we can make do with a suite of other sensors. But even he never said that LiDAR is not the best sensor. It's just that a couple of years ago he made a statement that it was too expensive. And he's right. A LiDAR used to cost between $8,000 and $200,000. Even at the low end, at $8,000, you cannot have a few of those in a vehicle. So basically, when people use expensive LiDARs, even when they were willing to pay for an expensive LiDAR, they only were able to pay for one, as you see on the Google car. When you have a single LiDAR, you cannot, you have to put it on top of the vehicle, up on a pedestal, to minimize the shadow effect and so on. And still, you're compromising in terms of seeing around the vehicle. And of course, you just paid $80,000 for that particular unit. Even when it's $8,000, that's still a big chunk of money just for the hardware. The vehicle on the bottom right, that's a Mercedes GLE 450 coupe AMG that our partner Daimler gave us. And our other partner Delphi reconfigured the fascia so it's IR transparent, and behind that are hiding two solid-state LiDARs. So when you buy the vehicle, it looks like that, like the red vehicle. Basically, you don't see the sensor, and that's the way it should be. We're not going to drive around with, you know, a lab bench on the roof of the vehicle. This is a simple version of our roadmap. First, we did build a mechanical LiDAR because it was easy and it allowed us to start developing the software. Our core product is the solid-state LiDAR. The first version is the automotive solid-state LiDAR, shown here as Gen 2. And I'll show it to you here. It's basically the size of 2 decks of cards. And 2 of those are hiding behind the grille of the red Mercedes that I showed you. This sells, I mean, this is not a sales pitch, but that's a key point for adoption. That's why I talk about the price. We were able to reduce the price, even for mechanical, to $1,000, but this is $250 in volume. And that's key. When we started the company, we talked to OEMs, automotive OEMs, and they told us, if you don't show us a roadmap that you're going to break the $100 barrier, don't even start the company. So we had to have a plan. So everything in here is silicon CMOS, old equipment, 100+ nanometer node, just really cheap stuff. However, the magic is all in the photonics circuitry that's robust, that has a high yield, that operates across a very wide temperature range, and so on. We have 5 types of silicon CMOS chips today inside this sensor. I'll talk about all of them. And long term, as you see in Gen 3, all of these chips being based on the same silicon CMOS platform will be integrated on one substrate. So the whole LiDAR will become one chip, and at that point it can go in a cell phone, it can be wearable, it can go in a helmet, and so on. It can go also inside every thermostat, behind every light switch in every home, and so on. The 3 main ICs A couple of those are PICs. There are not many conferences where I can say PIC and people understand what I mean. So photonic ICs, the optical phased array on the transmitter side, the SPAD array on the receiver side, the control ASIC on the transmit side, the ROIC, readout IC, with the TDC circuitry on the receive side, as well as the processor. This is the guts of the sensor, basically without the box. It has a receive side. The optical phased array, as many of you know, is basically a reconfigurable lens on a chip. The lensing effect is achieved by controlling the phase, which slows down the light the way you would normally slow down the light by having a different thickness of glass in a normal lens. So this is actively like a lens where at every point in an array of 1,000 by 1,000 or 1,000,000, at every one of these points, you can change, let's say it's a glass lens. It's as if you could change the thickness of the glass in a 1,000 pixel array. Since the lensing effect is built in, you don't need a lens in front of the receiver. So that's why in front of the receiver, there's no lens. There's just a flat plate. In front of the emitter, transmitter. On the receiver side, we have a SPAD array, a single photon avalanche diode, made in silicon. And you might say SPAD arrays don't exist in silicon. Well, that's also part of our IP. We make SPAD arrays in silicon CMOS. And that SPAD array is chip-to-chip attached to a readout IC, and then the output is sent to a processor. Much like phased array radar, optical phased array basically forms a radiation pattern by phase control. And you can control the direction, you can control the spot size if you have the right circuitry and capability to do that. Now, on the receiver side, we do quite a bit of signal processing to get high quality data and also to make our system basically robust against background light, robust against hacking, and so on. Some of the things we do. The first thing is TC-SPC, so statistical analysis of the data you collect. I'll show you how that works. We send multiple pulses, so each one of these LiDARs collects, we say 500,000, it's really 480,000 points per second. For each one of these points, we don't actually send a pulse, we send a pulse train, and that pulse train is coded, and it's a pseudo-random code. And we have a matched filter to see that the signal that comes back has the right code. And we do a number of other things, including spatial-temporal correlation. TC-SPC, basically, for every pulse, for every laser pulse that we send, we do binning. We have time bins where we collect, we're counting photons, right? This SPAD is a single photon avalanche diode. That's, by the way, the name of the company. The Quanergy is quantum energy because we count quanta of optical energy coming back at us. So that's how we came up with the name. So you're counting photon by photon, and you create this histogram, and you do statistical analysis to do the best measurement for the time of flight. There's the coding, so every time we send what I call, every time we collect a sample, we send a pulse train. In this case, for instance, the code is 1110010, and we apply a matched filter based on this code, and that tells you that allows you to pick out the signal from the noise. when you look at the light that comes back at you, it might look like it's just so noisy, it's just impossible to pick the signal out. But when you have a code like this, it's actually, it makes it very easy to pick out a signal from the noise. We look for temporal concurrency. So for each pulse train that we send, so for each 1 as opposed to a 0 in the code, we expect to measure the same time for the time of flight. If all of the 1s in the code do not give us the same measurement for the time of flight, we scrap that sample and we collect a new sample. A spatial concurrency. The SPAD array, you know, people who come from the camera world, the video world, they don't understand how a SPAD array works. It's not an imaging sensor. You're not imaging the scene on the SPAD array. The whole SPAD array just acts as one component that collects sequentially the measurements of the time of flight for each pulse, and the pulses are sent sequentially. So you have to hit multiple adjacent pixels in the SPAD array to say that you have a hit, and that's a spatial concurrency. Now, once you create this piece of hardware, the solid-state LiDAR, you can have lots of fun on the software side, because a lot of the capability and the algorithms can be controlled by software. In terms of, for each application, you decide how to react to the scene that you are sensing and what to do about what you're seeing. For instance, you see a deer in the middle of the road, you can actually alternate between looking at the big picture and looking at with the big spot, and looking at the deer to get a zoomed in view with the small spot. And you can alternate 1 point from here, 1 point from there, so on and so forth. So you keep your eye on the big picture, and at the same time you get the high resolution image of, in this case, the object, the obstacle that's in your path. So we also, because it's not a physical system, it's not a mechanical system. A mechanical system that's, let's say, a spinning LiDAR, you know, it scans the scene sequentially. Here it's random access. You can point in this direction, then disappear and appear in that direction without physically scanning in between. That's valuable in terms of giving you more capability. We can adjust. You have 480,000 points per second. You can adjust the window of interest. You might say in an autonomous vehicle application, I want to have very high resolution data along the horizon, so I actually have very high quality envelope of pedestrians and any objects that are on the road along the horizon. And I might use a larger spot looking up and down at lane markings, at bridge, and so on. We did the world premiere of this product at CES 2016. That was the world premiere. That's the first time we made it work, but it became a product that we are providing to customers this year. So at CES of this year, we did the product launch, and we actually received the Best of Innovation award from CES. And that's the spin that I wear every day. Yeah. One of the very exciting and very innovative products that we showed at CES was this headlight that we jointly did with Koito. Koito is a Japanese headlight maker. It's actually the largest headlight maker in the world. They make headlights for Toyota and other companies, actually also for the VW group. And in this case, Koito built this LED headlight with 2 of our solid-state LiDARs built in it. In this case, they used our smaller LiDAR. We have a smaller LiDAR. So this one is called the S3. It just stands for SSS, solid-state sensor. People think, oh, it means the 3 dimensions, or it means it has the 3. No, just. And this is called the S3 Qi. Written QI. We developed this for drone applications, robotics, any application where size, weight, and power consumption, power draw basically because you're running off a battery and so on are critical. So this can already go inside the helmet of a soldier or a firefighter. So this is the version that they integrated two of in this headlight. You see one here, one here. How much time do we have? We're doing okay. In terms of levels of automation for on-road vehicles, you hear about level 1 through 5. Level 1, basically the vehicle gives you some level of driver assistance, and level 5, the car fully drives itself. The car comes without a human being in it to pick you up. When you drive to work, you can take a nap in the back. That's level 5. Let's not worry about when or whether level 5 is going to happen. At this price point, even for level 1 automation, this makes sense. So we don't stress too much about whether level 5 is going to happen really or when. The most exciting level is level 4. The industry already had level 1, level 2 quite a bit. If you have a high-end vehicle, you already have lane detection, adaptive cruise control to keep the distance from the vehicle, and automated parking in some cases. All of that is level 2. In my opinion, the industry is going to skip level 3 because level 3 is the most controversial one. That level 3 is the one that requires you to take control when there's a situation that the car cannot deal with. And that's not acceptable in my opinion. I think the industry should skip level 3. Most of our customers are talking about skipping level 3. Some of them actually are doing level 3. It's their decision, it's their responsibility. Because some people say, I don't mind taking over when the car tells me that there's a situation it cannot deal with. Yeah, but usually when someone says that, they might be, they're typically very athletic and young and so on. I tell them, yeah, but if someone is in a vehicle and usually I say if an older person takes a nap and the car says, okay, take over now, it's different, right? So just because you think you can handle it, you cannot just sell a car to everyone that tells you that you have to take over when there's a difficult situation. So in our opinion, level 3 should be skipped and go straight to level 4, and that's the main level of automation that makes sense. Essentially, the vehicle drives itself in most situations, and in some situations you drive the vehicle, but there's no mix of the car is driving itself, then it asks you to, hey, help me out. When you look at the whole system, the whole perception system in the vehicle, there's data that comes from the LiDAR, so the point cloud with essentially that gives you an envelope of the environment, a certain frame rate. You have information from other sensors, IMU, GNS, and so on, and other vehicle data. And when you add context based on pre-existing map and so on, you can now do some perception, and you can do multiple layers in the perception pipeline. So you do the data formatting. The first thing you do is you do ground plane detection, then you do object detection, classification, tracking, and out comes an object list, which is basically tracked objects. And and then you can deliver that with a solid state LiDAR because it's not mechanically spinning. You can go to 10, 100, even 1,000 frames per second. And that's what most OEMs want. Most automotive OEMs want basically that you hand them this object list. For every frame, tell them there's a person here the curb is right there, there's a cyclist there, and so on, and say, do that maybe 100 times per second, and they will decide how their car will behave based on their brand and their willingness to take risk. And Tesla has a mode called the insane mode, right? So clearly Tesla has kind of a certain pedigree and culture, and they think that whoever buys them has a certain, enjoys being in a car that drives in a certain fairly aggressive way. But when you're in a Mercedes S-Class, maybe you want more luxurious behavior, and given a certain situation where a Tesla might decide to pass, the Mercedes S-Class might decide it's not worth kind of shaking up the person and kind of creating all that, just really kind of applying lots of torque and doing this crazy maneuver, because people who buy Mercedes S-Class tend to just want luxurious, more luxury than sport behavior. Just a visualization of what basically what you see in every frame, which is ground detection in green, a vehicle in this case in red, a bicycle or a bike in magenta, a pedestrian is in yellow, and the stationary objects, or trees in this case, are in blue. But that's not what you show the driver. The driver is not going to look at this and make decisions. This is a visualization of the information that we give to the OEM so they can make decisions. Now the LiDAR is the primary sensor. People say you're going to always use LiDAR, radar, and video. We agree. However, it's critical to agree also that the LiDAR has to be the primary sensor, which means it's the sensor that's in charge of perception, localization, and navigation. No other sensor is as capable. This shows a configuration of a LiDAR, radar, video system by our partner Delphi. This data was actually collected by NVIDIA using our LiDAR. First, this was a first pass up 101 in the Bay Area. So first they did the 3D mapping. Then the car was driven in a mode to actually drive itself. So first thing, it did what's called an occupancy grid, the detection. You basically you do perception and you figure out what's where and at what speed are they moving and so on. So you collect that kind of information at the rate of 10 or 100 or more frames per second. And once you do that, now you can do a path planning. In this case, you see this red line here, this is the path that the car has decided to take given these vehicles and how fast they're moving and so on. And once you've done the path planning, you navigate, you activate the controls, and the car takes over and it controls the acceleration and the steering and so on. This is a 3D composite point cloud that we collected just with a single pass around the block that's next to our headquarters in Sunnyvale. The data is so rich that there's not enough resolution on this screen. If you zoom in, you see this kind of cross-section. As you can see the curvature of the road. You can see the trees. You can even count the leaves on the trees if you want. You can see the lane. This is color-coded based on height. You can even see the lane markings just based on the thickness of the paint, because when you drive by and you're as close as possible to the lane markings and they're just a few feet away, we have sub-millimeter resolution. But you can also visualize the data based on intensity, which is a representation of the reflectivity of objects. And in this case, any retroreflective features really stand out, such as lane markings, right turn signals, stop sign. We can also do an overlay between the point clouds that we collect and the satellite imagery for positioning. So that's all I have in terms of presentation. Those are our 10 locations globally. We are hiring, basically 5 people a week. So in all areas, if this is exciting to you. But more importantly, maybe, if you're an expert in the space, you want to start a company and so on, you know, it's a good time. I mean, in the late 90s, we all kind of got into telecom and fiber optics and so on, and optics was king, and optics is king again now because of this particular application of autonomous vehicles, which is arguably the hottest space in technology. So thank you very much. I'll take a few questions.